All right. Yeah, maybe we get started now. It's 4 o'clock from my time. Um, Good afternoon, or good morning, good evening. Welcome to the Topology Optimization webinar. It's wonderful to see many familiar faces as well as many new names. So welcome everyone. Today, our session is about multiscale topology optimization. Let me share my screen. So our session today is about multiscale topology optimization. In my opinion, multiscale topology optimization is one of the most intensively researched topics in our community. In the past, we have organized 2 sessions on related topics already. So in 2022, Professor Shelly Zhang from University of Illinois at Urbana, Champaign organized a session on topology optimization for architectural material and multiscale structures. Shelly will also give a talk today. Last month, Professor Wei Chen from Northwestern University organized a session on data-driven multiscale design. Both sessions were very well attended. If you have missed any of those sessions, you can watch the recordings on YouTube. This is our schedule today. Following our new format, we start from presentation of one review or education paper. Today, I will present the review article that I wrote together with Ole Sigmund and Jeroen P in 2021, published in Structural and Multidisciplinary Optimization. Following that, Rebekka Woldseth will present her recent work on phasor noise-based dehomogenization for 2D multiscale topology optimization. And Shelly will present her recent work on topology optimization of irregular multiscale structures. The duration of the seminar is 1 hour. Between the talks, we will allow 1 or 2 short questions, and we hope to leave about 10 or 15 minutes at the very end to answer your questions. During the presentation, if you have any question, feel free to write the questions in the chat. We will try to answer. All right, so as a disclaimer, my presentation today for this review article is more like a graphical journey. I use many pictures from the literature. I think only on one slide, I have some equations. I try to minimize the number of equations. In our review article, Jeroen made a very beautiful mathematical categorization of different approaches. In my presentation, I deviate from that categorization, but to show you what kind of structures can be designed with multiscale structures and what was the motivation, how it was evaluated, and what was the benefit. Of course, topology optimization multiscale has been intensively researched over the past 3 decades. I'm not able to cover the entire spectrum, so many papers, especially published in recent years, might not be captured in this review article published in 2021. So looking at multiscale structures, which is not common, both in nature and in engineering, it is very commonly seen. For instance, on the left-hand side, you see the cross-section of the bamboo, and on the bottom, you see the cross-section of the femur. In both bamboo and femur and many other biological systems, we can identify porous structures. And if you look at closely, these porous structures, they are not uniform. At different locations, they have different porosity. And looking at the femur, it even has directional effect. So it is anisotropic. For instance, here you see the microstructures in the femur, and they are very well aligned with the principal stress directions. Multiscale structures are also often used in engineering. For instance, in the Eiffel Tower, if you look closely, you can observe three levels of hierarchies in this Eiffel Tower structure. So it is made of many beams, and within the beams, it is made of further smaller beams. In both nature and engineering, the multiscale structure creates lightweight design. And also the manufacturing process in nature and in engineering, it means lightweight design means less energy used to process the material. And for locomotion of animals, for vehicles, it means less energy to transport these structures. A benefit of lattice structures or multiscale structures is it is robust. in a biological systems, the bamboo has to withstand forces from different directions. The femur has to support our daily activities where during our running, during our sitting, the force we applied to the femur is different. And because of this different loading cases applied to the structures grow in a way to be robust to different loading conditions. And this principle is also useful for engineering. And there are many more benefits beyond structural mechanics. In a review article, we focus on structural mechanics, so I didn't elaborate more on other benefits. This is a brief history of the development of multiscale topology optimization. On the bottom left, in gray, I indicated the mathematical foundations that were laid down by pioneers in this field in the 1970s, 1980s about the existence of solution, the optimum rank n laminates, homogenization theory. I'm not going to discuss this, and that's the reason I use gray to indicate this mathematical or theoretical foundations. The starting point with multiscale topology optimization, I would say, is the seminal work by Bonza and Kikuchi published in 1988. They proposed a homogenization-based topology optimization approach to optimize the distribution of unit cells with a rectangular hole. And these unit cells, they use numerical homogenization to evaluate the equivalent mechanical property and optimize the distribution of these unit cells. And this becomes the beginning of topology optimization as we know of today. But the structures within these rectangular holes are difficult to produce. So in the 1990s, many algorithms or many researchers proposed to use a density-based approach or to use to optimize the distribution of solid material instead of unit cells. And this is now known as density-based approaches. For instance, from 1989, Bonza proposed to optimize these grayscale elements. And since late 1990s density-based approach, the focus shifted from homogenization to density-based approach. First of all, it's easier to produce, not without challenges, but compared to homogenization-based approach, it becomes closer to the possibility of manufacturing, and the mathematical side is also more simplified. At the same time, in the 1990s, other approaches optimizing solid materials have been proposed as well. For instance, the evolutionary procedures by Xie and Stefan in 1993, and level set approaches also optimizes the distribution of solid materials. So because of this reason, I use the same color to indicate they belong to a broader same category. In the 1990s, it's also important to notice this inverse homogenization, which becomes very important to design optimal microstructures. It is also used to design multiscale structures, as I will explain later on. A bigger change to the picture is additive manufacturing comes to the picture in around 2010 or before or slightly after. From 2010, there has been a lot of research on multiscale approaches. These approaches include concurrent optimization, de-homogenization, or using local volume constraints, data-driven approaches, for instance. And this is the focus of the review article. From a manufacturing perspective, if you visit a 3D printing exhibition, you will notice many structures, they are designed by topology optimization and manufactured by additive manufacturing. The manufacturing industry, they really embraces this technology to showcase the unique possibility to fabricate complex geometries. You may also notice in the additive manufacturing industry, it also produce a lot of lattice structures because inherently it is lightweight because of its porous geometry. The motivation to create multiscale structures from additive manufacturing perspective is to combine the benefits of organic geometry from topology optimization and the low density from lattice structures. as shown on the right-hand side. This is a graphical summary of the techniques I'm going to present in this talk. The foundation, I would start from density-based approach because it is related to many of the approaches that are later researched. For instance, full-scale approach, material interpolation, to some extent, is also related to the hierarchical or concurrent approaches. And to the end, I will present this de-homogenization approach. In density-based topology optimization, we discretize the design domain into elements, and each element carries a design variable either to be 0 or 1, indicating without or with material. And this binary optimization problem is relaxed to allow the design variables to continuously change from 0 to 1. So if we have a look at this animation, and these intermediate densities are displayed in gray. As the optimization continues, it is solved in an iterative process. As the optimization continues, it converges to a black and white design. And here the objective function is related to the design variables, the pseudo density, the response of the structure, the displacement in this case. It satisfies the equilibrium equation, the stiffness times the displacement equals to the external force. And there are some constraints. For instance, the total volume constraint prescribes how much material can be used in this optimization problem. Starting from here, if we increase the resolution, for instance, as shown in a paper by Niels in 2017, he optimized the wing structure using 1 billion finite elements solved on a supercomputer with 640 CPU cores. And if we can simulate the structure and optimize it at this high resolution, we can create already very fine geometric details. Here I call it full-scale approach because in this approach, we don't make assumption of separation of length scales. And this is in contrast to many multiscale optimization approach, which makes use of homogenization, which is based on the assumption of the separation of length scale. By increasing the resolution, we are already able to create fine geometric details, but it has the consequence of requiring a lot of computation. And because of this reason, there are also algorithms proposed to create structures with geometric details. For instance, in 2006, Zhang and Sun proposed an algorithm to create a structure with a repetition of patterns. For instance, on the left side is the design domain. The left edge is fixed. The force is applied on the right side, pointing downwards. Using the standard density-based topology optimization, you will get the design in A. It has a compliance of 156. And in the design domain, you can also restrict the left side of the domain to be the same as the right side of the domain by using the average of the sensitivities. And in this way, you create a pattern with the identical left and right sides. And since the design variables is reduced, the solution space is reduced, and consequently, the compliance becomes larger, which means the structure is less stiff. If you further increase the number of patterns from 2 to 4, the compliance further increases. And eventually, if you increase it to like 20 slices, repetitive patterns, the compliances will be very big. What's so interesting in this result is if you look at the bottom right with a lot of repetitions, the microstructures becomes like a cross structure, X-shaped cross structure, because the structure has to support forces from different directions in the best way, and they are not allowed to rotate, so they become a standard X shape in this case. A variation of this pattern repetition is to create graded patterns. So for instance, you can have patterns with vary in size. So here on the bottom, the pattern is larger, and gradually the pattern becomes smaller, but they follow the same topology because the variables, they are linked, they are scaled in this way. And this pattern repetition or pattern gradation can be easily extended to 3D. So here you see 3D results with this pattern gradation used for architecture purpose. Continue with full-scale approach. A different way to encourage the appearance of fine geometric details is to deviate from the total volume constraint, but replace it with a local volume constraint. So here, these two animation shows optimization applied to the same boundary condition. So a single load case with the standard topology optimization, you will get a solid structure in the middle and empty space here. And with local volume constraint, it tries to spread the material as much as possible. Consequently, the structures have many microstructures. And if we compare the porous geometry from this local volume constraint and the stress distribution, there's a very good alignment with these stress directions. Again, these full-scale approaches can be easily extended to 3D. In this case, the computation will be higher in 3D, but the algorithm itself is the same. So on the right side is a famous shape optimized by this algorithm and produced with 3D printing. There are quite some recent developments on this local volume constraint. For instance, to simultaneously optimize the shell and microstructure inside. So here, the shell and the internal structure, they are optimized simultaneously. This is half of the simply supported beam. An issue with this local volume constraint is it can converge very slow. For instance, if we have a design space, it's a circular shape, we have on the boundary, we have uniformly pressure. And in this case, it has really has difficulty to converge. So after 400 iterations or even after 1,000 iterations, the middle still remains to be gray. And if we analyze the topology of the stress tensor field, we can identify some topological features. And by embedding these topological lines into the optimization, it encourages the appearing of solid structures. So on the bottom two rows indicate compares with different initialization how the optimization converges faster. I need to look at the time. So that's a full-scale approach. Starting from a density-based approach, you can also optimize the distribution of unit cells. For instance, on the left-hand side, by density-based topology optimization, you get this solid structure. And if you don't have solid structure, don't have solid material, you replace it uniformly with the same unit cell and doing some trimming operation, you will get a two-scale structure shown like here. An approach that has been experimented in the manufacturing industry is to use a low panelization with P equals to 1, and you will get a gray structure. And with this gray structure, people map microstructures with net porosity and to create this graded porous geometry. And this means the panelization is not high enough to converge to black and white. It also is an overestimation of the stiffness. So if we do a careful evaluation of different penalty value, so in this comparison, in the bottom middle is a standard topology optimization, density topology optimization with P equals to 3, and we'll get a black and white structure. And if we have P equals to 1, we have a gray structure, but this gray structure overestimates the stiffness, so the compliance is small. But if this grayscale structure is to be replaced by a square shape or with a X shape, if we evaluate the compliance again, it is actually very bad. So the realization with a p equals to 1 is not recommended. If you use a square shape as the unit cell, we recommend to compute to use numerical homogenization to evaluate the elasticity tensor and to plot the curves, and using polynomials to approximate the curve, the relation between elasticity tensor and the specific porosity of the unit cell, and use that to replace the simple interpolation. That will give better results than using p equals to 1 and replace the gray elements. So with density as a design variable, each unit cell has only one design variable. There have been a lot of research on to extend the solution space by allowing multiple design variables within one unit cell. For instance, in 3D, if you have these diagonal structures, and each of the diagonal can have an individual thickness. So in this case, you would have 7 design variables per unit cell. This increases the solution space, but it also means it requires a lot of pre-computation. If each lattice has one design variable and you use 10 different values, and because we have 7 design variables, it will require you perform numerical homogenization 10 to the power of 7 times, which is huge. You could also design different unit cell. For instance, on the right side, you can design a unit cell like this to change the thickness as well as to change the amplitude, and this allows to create unit cells that continuously change from negative Poisson ratio to a positive Poisson ratio. You can also use inverse homogenization to design the microstructures. Shown here is we have grayscale from 0.1 to 0.8. And if you use this volume fraction to design unit cells, each of the unit cells is optimized. The problem here is if you place 2 unit cells together, they are not necessarily form a good collection because the unit cells, they are individually optimized. I'm saying this also hindering a solution to this. So in a work published by Gardner in 2019, we proposed to optimize the multiple unit cells together, optimizing the extended boundary instead of the small domain of each unit cell. And with this, it encourages the collection between the unit cells. If we optimize multiple of them or 8 of them together, in comparison, you see the collection is much improved. We can even plot this collection to compare it with the theoretical bound. So if without this, if the cells are individually optimized, and if you look at 2 cells together, the stiffness is very bad. But if we optimize together, it almost reaches the theoretical bound. Another popular approach is hierarchical or concurrent optimization, first published by Rodriguez in 2002, and there are many follow-up works. We have also worked on this topic in the past. From the results shown here, you see we do get a lot of microstructures, but these microstructures, they are not very well connected. With this compound formulation proposed by Gardner, the collectivity is improved, but it still looks a bit weird. It's still too much variation in the curvature. So my personal opinion is the hierarchical approach has the potential to improve speed, but the full potential is still to be validated. Then comes to dehomogenization. And this relates to the seminal work by Bonza and Kikuchi. And the basic idea is to optimize the distribution of unit cells parameterized by the rotation of the unit cell as well as the thickness of each of the 2 sides. And from homogenization-based topology optimization, if you put these unit cells side by side and rotate, you can observe they are kind of connected, but from a structural perspective, it is not it is not the best. The question to be answered in dehomogenization is how do we interpret the results from this homogenization-based optimization? There are two directions. One is to use image-based approach to optimize the density or to optimize a scalar field, requiring the gradient of the scalar field to be aligned with the optimized orientation of the unit cell. So this was published in 2018. So on the left side is just overlapping unit cells. On the right side is compiled geometry from aligning the fine scalar field to the orientation of the microstructures. And this was pioneered by Punch and Trabelsi in 2008. After 10 years, it has become picked up again and improved, and it becomes a very popular research direction. So later on, you will see Rebekka will present her work on Phasor Loess-based homogenization, and Peter Jensen at the DTU also did a lot of work on dehomogenization under multiple load cases and to extend it to 3D. A geometry-based approach, the idea is to use geometric meshing algorithm to transform this frame field into a continuum structure. So here you see in the middle is the optimized orientations. On the right side is a geometric structure from the meshing algorithm, which the requirement is in the meshing, the edge of each mesh should be aligned with the optimized orientation. Again, this can be extended to 3D and to multiple node cases, as recently published by Wang. The last slide to conclude, there have been a lot of developments in multiscale topology optimization, and in the review article, we have focused on structural mechanics, but there are many more problems to be addressed. For instance, to consider stress, consider buckling, nonlinearity, or plasticity, go beyond structural mechanics about acoustics, optics, thermodynamics. And most of the structures we have been saying is about two scales. Within a structure, you have some substructures. Should be also possible to extend to multiple scales. In nature, it is the maximum is 7 scales, and in topology optimization, this large number of scales is yet to see. Also, manufacturability has always been a problem to consider. At the end, we recommend thorough evaluation of new algorithms. For instance, if separation of Nernst scale is assumed, because the separation of Nernst scale is assumed if you use numerical homogenization, but the results might not agree with full-scale analysis. For full-scale analysis, one can use the MATLAB code from Amir and Ole, Amir and Niels. They have a geometric multigrid solver to solve at a very high resolution, and that full-scale analysis can be used as a benchmark to evaluate how valid this separation of Nernst scale is. If solution space is reduced by parameterization, we recommend to compare with optimal rank 2 material. And in a review article in the appendix, Jeroen provided the MATLAB code for this optimization problem. But in general, we recommend to validate multiscale structures either numerically or experimentally. All right, this concludes my talk. I have noticed I already run over time. I would suggest we move on to the next presentation. I will try to answer questions or during the presentation or at the very end. All right, so maybe Rebekka, you can share your screen.
Yes, perfect. Can you hear me?
Yes.
Okay, oh good then. Thank you, Jun. So yeah, and also thank you for inviting me to present my work on phasor noise for dehomogenization in topology optimization. Yeah, my name is Rebekka. I'm currently a postdoc at DTU in the top-opt group. So I don't have to spend that much time on the concept of dehomogenization now. Jun just gave a pretty good or really good introduction to the topic. So de-homogenization, we basically start from the optimized homogenized solution, considering these rank n laminates, which are given layer-wise by sets of thicknesses and orientations, with an underlying assumption of infinite constant periodicity and perfect microstructural bonding. The goal of the de-homogenization approach is then to obtain this single scale interpretation of the solution while staying as true to the homogenization assumptions as possible, where one of the main challenges is this balance between conformality with respect to the orientational field and linked scale control and maintaining consistent unit cell sizes. So the method presented in this paper is based on Phasor noise from computer graphic and was developed a few years back at India in France. It's a procedural noise function, which means that it is compactly parameterized and can be efficiently upsampled to fine resolutions of these very detailed patterns with localized control of orientation and periodicity. The parameterization is based on a finite set of Phasor kernels, where each Phasor kernel is defined by sort of its location in space, as well as the orientation and frequency of this wave type signal that is emitted from this kernel in space. And the signal strength is dampened by a localized Gaussian kernel. From this compact Phasor set, the sampling of the Phasor noise field can then be conducted by summing the signal responses at any point in space, depending on what you want to sample, what the domain is. And due to the Gaussian kernel weights and the signal being complex, you get sort of a weighted average by summing the signals such that you get smooth transitions between the different kernels in space. And the reason that Phasor noise is quite interesting for de-homogenization is that if you consider this grid of kernels that is placed at the nodes in this grid, and they have been attributed an orientation, you have that the tangential wave field is a trivial solution, but the normal waves as sketched below becomes non-trivial, and therefore there is a trade-off between periodicity adherence, orientation adherence, and also connectivity. By directly sampling Phasor noise, you can see that these bifurcations that look sort of like branches are introduced to better adhere to periodicity while trying to adhere to the orientations, but it is also quite evident we're still quite far away from the sketched solution. To this end, the original works on Phasor noise introduced phase alignment and a sampling filter, which are where the phase alignment is focused on improving the kernel compatibility by aligning the waves emitted from neighboring kernels such that you reduce the destructive inference. And the sampling filter is introduced into the Gaussian sum to better adhere to the orientations and get a smoother noise or pattern out. So for the Phasor-based de-homogenization, the underlying conceptual idea is that consider these rank n laminates in a layer-wise fashion, where each element in the multiscale optimized solution is directly translated to a set of Phasor kernels. And from these Phasor kernels, you can sample the Phasor noise at any resolution and periodicity you desire. And then by wave field transformation of the complex Phasor noise, you can obtain sort of a level set type representation of each lamination layer, which can be directly projected to solid void based on the local relative thicknesses. To illustrate the concept using just the baseline Phasor methodology for de-homogenization, I have here illustrated a cantilever beam, where you can see that the infill follows orientations quite well and also adheres to periodicity, but due to these bifurcations that are introduced in the field, you get disconnections and local curvature, which are detrimental to the structural performance. So we are still more than 34% away from the multiscale solution. To this end, one of the major procedures introduced in the de-homogenization paper is how to connect these disconnections. And the method benefits from the fact that we know that these bifurcations are located at singularity points in the sampled phasor field, so you can find them directly from the noise you have generated. And by considering the real valued wave transformations, you can introduce phase shift manipulations to sort of solidify the branches, and by image morphology operators locally pinch them to reduce the material to these more structurally beneficial V-shaped branches, which makes, and as this can be done locally, the procedure is very efficient, and as you can see, also improves the structural performance immensely. The second improvement introduced is the addition of a structural boundary, which is also based on phasor concepts, and is generated by placing phasor kernels along the boundary of the multiscale material indicator field. And these kernels can then be assigned orientations based on the gradients of this indicator field, such that you can sample sort of a wave covering around the boundary of the structure that can be transformed and thresholded similarly to a lamination layer. The final major improvement introduced for de-homogenization is the addition of anisotropy. And in this case, anisotropy is considered as modifying the impact of a phasor kernel, where it is increased along the sort of direction of the laminations and reduced normal to the laminations to limit the amount of curvature around the branching points. And anisotropy introduced in the phase alignment helps improve the distribution of these bifurcation points to better facilitate closing V-shaped branches, which are more mechanically sound. And the adding anisotropy in the sampling, so the kernel signal impact, also improves the V-shaped nature of the branches before closure, which has a significant improving effect on the final dehomogenized design. And just a brief summary of some of the results from the article. So the procedure was compared to some of the other leading sort of in-house methodologies for de-homogenization, where it was found that the phasor noise approach offers a really good alternative in terms of solution quality and computational time trade-off, as well as a proof of its scalability and promise for more complex structures and problems. There was also observed an increase in stability and robustness in terms of handling problems with singularities or other artifacts in the orientation fields, as well as structures with small holes or very thin structural features. And due to the layer-wise handling of the rank-n laminates, the procedure can be extended to any rank-n problem, which is here exemplified by rank 3 multi-load cases. So this is sort of what we're working on now with this phasor noise, and it's the 3D extension. Conceptually, the idea is very similar to 2D due to the phasor formulation being defined based on location and orientation, which means that you can more or less just add the third dimension in a conceptual manner. But as with anything else, when it goes to 3D, you go to 3D, there are some implementational challenges and other considerations that significantly increase the complexity. And just as a small teaser here, I've included some preliminary results for some of the structures we are trying to homogenize. Here I've included the slotted tower, where the very promising preliminary results shows that we are within 6.1% of the multiscale solution, which is considered quite very good. And here the Phasor-based formulation is applied to an infill cantilever problem, where we are within 2.8% of the multiscale solution, which is really good considering the relatively coarse length scale it's realized on. And this is just further advertisement of what's to come, showing the flexibility and complexity the Phasor noise can handle. And that was more or less my talk, with a final little promotion of our upcoming educational code, which is implemented in MATLAB, that will facilitate this integrated framework between multiscale topology optimization and on-the-fly de-homogenization to make it more accessible to start working with these concepts. Thank you.
Wonderful. Thank you, Rebekka. Any quick question? If there's no question, then we move on to the next presentation and we answer questions at the very end.
All right, let me share the screen. Is it visible?
Yes.
Okay, perfect. Right. Thank you, Jun, for the very kind invitation. And today I'm glad to present to you our recent work published in CMME on topology optimization of irregular multiscale structures with different types of responses that's tunable using a virtual growth algorithm. This work is done with my PhD student, Yingqi Jia, and Chris Liu, assistant professor from Peking University. So here I listed a few recent examples of the multiscale structure methodologies in the literature. Because there are many methods to design the multiscale structures with different functionalities, and Jun gave a very nice introduction and review of different methods. So here I just want to show some recent examples. And before we introduce the framework that I'm going to talk about today, let me formally define what is the virtual growth. So let's suppose we have a few building blocks across rhombus, arrow, and corner. Let's say we want to build or grow as architecture using these four building blocks, just like playing Legos. And for each of these building blocks, there is an associated probability of it showing up in the structure. And here we call this a frequency hint. Let's say 30% of this block, 20% of this, 30% of that, and then 20% of the grid. Using these two information, building block and frequency hints, there's a recent algorithm proposed by this the science paper on the bottom that can virtually grow architecture based on these two rules that we just defined. It's called virtual growth algorithm. It's the entire process is like growing of a plant. So a natural question to ask is, how do we optimize a structure made of this irregular material that can virtually grow? So that's what I'm going to present today. So here is an overview of our approach. So suppose we have this design domain, and we are working on some different objective functions. It can be displacement control or controlling the energy distribution in a domain, or even maximization of the stiffness. For that, in the macro scale or the structural scale, we are optimizing based on the information we have. We optimize both the topology with or without material, as well as the distribution or which building block we are going to select by optimizing the frequency hints that it has or the probability of showing up. And then based on the optimized frequency hints and the density, we grow the microstructure and form this multi-scale structure based on the virtual growth algorithm. And finally, we can 3D print it, we can fabricate it and study it. So to achieve this entire framework, we need to address two different things. The first thing we need to address is to generalize the virtual growth algorithm, because the classical virtual growth algorithm will grow the architecture based on the homogeneous frequency hint combination. And here we need to generalize it so that it can account for heterogeneous distribution of frequency hints across the domain. And the second thing we need to tackle is we need to know the relation between the frequency hint and its corresponding homogenized mechanical property. So let's do that one by one. So the first one is we want to extend the virtual growth algorithm to account for multiple or heterogeneous optimization guided frequency hints. Let's say we have this mesh, the finite element mesh. We have 2 by 2 element. For each of the elements, we will have a distinct frequency combination, the probability of each building block showing up. And in this case, we'll need to, based on each of the optimized frequency hints, we'll need to grow the material correspondingly. Let's use this top left as an example. Let's say we have these 4 building blocks. The first thing we need to do is to form this adjacency rule and adjacent table. The main idea is to know which building block can connect to the other one without having some hanging members or have some fully detached structure. The second step is to decide how many building blocks we're going to fill per finite element. So in this case, let's say we want to fill 3 by 3 or 9 in total building blocks according to the optimized frequency. And then we gradually fill in each of these locations, and we use the lowest entropy. We compute the entropy information of each of the cell, and we decide where do we fill in based on the lowest entropy information. And then the building block type will be generated based on the optimized frequency hints from the optimization. So we fill in this building block 1 by 1, and also we fill in each finite element 1 by 1, and we'll grow the entire structure finally. So now we know how to virtually grow the these building blocks in the whole domain. The next step is what is the relation between the frequency hint and the building block? So basically the constitutive relationship. So here we achieve that using a data-driven approach. We will begin by prescribing 4 building blocks, that the one that I just showed in 2D and another 4 in 3D. And then what we will do is we will uniformly sample the frequency hints in hyperplane. And then we will generate the corresponding architecture following this generated frequency hint. And for each of these structure, we will use the numerical homogenization methods to compute the homogenized elasticity. I will skip all the details for that. If you're interested, that's listed on the bottom, the paper in 2012 in CMME. So essentially, we computed the homogenized elasticity component, and then to visualize the space of the material property, we define this average Young's modulus and the Poisson ratio for both 2D and 3D cases, and then we visualize this both of these material space in 2D and 3D. And we can see in the 2D we have relatively decent coverage of the space, and for the 3D we have this coverage. So after we generate the database, we'll train a fully connected neural network that takes basically the frequency hint and will predict the independent component of the elasticity matrix, which will give us the continuous and differentiable constitutive relationship. And we do that for both 2D and 3D. And as we can see, we verify the accuracy of the neural network model using in 2D and 3D, and we can see both the training data and the test data are matching pretty well with the ground truth. All right, so having the constitutive relation established, now we are ready to formulate the optimization formulation. So the design variable will include two things, as we mentioned. One is the density variable. Another set is the frequency hints. Because we have 4 building blocks, we have 4 set of frequency hints. And in terms of the objective function, we work on various different types. It has the displacement control, has the energy, straight energy density distribution, or maximization of global stiffness. So for constraint, we have the commonly used volume constraint and the minimal stiffness constraint. And they are used for some example. All right, so finally, we have the static equilibrium, and the elasticity tensor is calculated through the SIMP, as well as the machine learning model that we just established. All right, so let me show you very briefly some quick examples of how it works. The first example in 2D, our goal is to control the spatial distribution of the strain energy in this disk. So we want this part, the blue part, to have this number of strain energy density, and the yellow one has this amount of strain energy density. In this optimization, we optimize both the density as well as the frequency hints of the building block. So here is the optimization history. We can see both the topology as well as the frequency hints are being optimized. So here is just a sample point from this here. And finally, we can see that the stress, the energy distribution matches pretty well with the target ones. If we compute the structural performance, we can see the strain energy indeed matches pretty well with the target one. So with the optimized frequency hint, we next virtually grow the structure that we just optimized. And let me try to speed it up. Okay, so basically, finally, we'll have this structure fully growing, following the optimized virtual growth algorithm. One thing I want to point out is that because of the use of the virtual growth algorithm, each local member, we ensure the local connectivity without using any additional constraints. Finally, I want to quickly show a demonstration in 3D. In this case, we have a sphere, and we are also optimizing both the density and the building block types, or the frequency hints. Here we optimize the stiffness of the structure, but I want to point out that this choice of the objective function is only to demonstrate the generality of the framework, because this choice of building blocks is by no means optimal for the purpose of maximization stiffness. Okay, so here is the optimization history, and we can see that it fully converges at the end for the objective function and the constraint. And based on the optimized frequency hint, we virtually grow this structure. So it's taking some time to grow. And we also 3D printed the structure just to demonstrate that it can indeed be fully connected, and we can obtain the structure without too much effort, because each building blocks can help us to ensure the minimum length scale. And here are some zoom-in views or different views for the irregular 3D architecture, and we identify this building block from some local location, each of these 4 types. Okay, so finally, some quick remarks. We show topology optimization framework based on the virtual growth algorithm to design the aperiodic and irregular architecture. So this architecture will have building blocks that have optimized and spatially varying frequency. So they're optimized to allow different types of structural response control. And also the designs can show explicit control for the feature size, as well as the guaranteed connection because of the virtual growth algorithm. And also I want to point out during the optimization, the frequency hints can be fully mixed. So in a sense, we don't need to penalize it in order for it to have to choose from 0 to 1. So the design variables can be fully mixed because they represent probability. And finally, I want to point out the last but not the least, the choice of the building blocks can be quite flexible in the sense that here we just select 4 building blocks that would work. But if we can certainly just choose another set of building blocks as long as the minimum connectivity requirements are met. So the design space can be made much larger than what we show here. So with that, I'd like to conclude.
Thank you for a nice presentation, Shelly. We have a few minutes for questions.
I have a question for Shelly. So thanks for a nice presentation. I was just wondering, when you have the cells for given percentage of the different sub-units, there are many different ways to realize it. So what is your variability in the effective properties for a given distribution of the cells?
Yeah, I was muted. That's a great question. We have some convergence study to study the variation of each realization, and we found out that it really there are 2 points. The first thing is will depend on the building blocks that we select. So if the building blocks that are is more regular shape instead of irregular, then the variation will be not as much as we seen. So let me quickly show this one. Okay, yeah. So basically, we show this convergence study, and for each of these number of building blocks, we have five realization of these same optimized frequency hint. We can see among them they don't vary too much for different number of building blocks per finite element. And part of the reason is because these building blocks are quite regular. It's not very irregular. In this case, we don't have too much variation for each realization. And if we use a different irregular building blocks, we will expect that the variation will be much larger. But in the case when we have a very coarse, or we have a few building blocks per finite element, we have done a study with a more irregular building blocks. We can see in the beginning we have a lot of fluctuation, but at the end, when we have more towards the separation of length scale, we see the variation becomes much smaller than the previous ones. So hopefully that answered the question.
Thank you.
Yeah.
I have a question for Rebekka. Rebekka, you showed some 3D results. So all the structures they look like a closed wall structure. I'm wondering whether it is possible in the phasor noise formulation to allow to make sure there's all the holes are collected somehow to create some open hole structure.
Open hole structure.
Open wall structure.
Open wall structure. I mean, it depends on the structure, I would say. Like, I mean, for the Lotte Tower I showed is very thin, right? So it sort of relies on the boundary to be connected, but
yeah, for the cantilever, I saw many parallel wall-like structures.
yes, yeah, because it's supposed to be closed wall, right? So it's only got one layer active, but you would need multiple layers to guarantee structural soundness out.
So from a structural perspective, the closed wall structure is stiffer, but from a manufacturing perspective, there are benefits to make them open in order to allow the fluid or powder to be removed, for instance.
Yeah, I'm not that familiar with how open they would have to be. I mean, so, but the boundary is added outside, right? So you can control, you can also modify how you want the boundary to look if you not want it at all. So Yeah, sorry, I don't think I understand the question.
I could add a comment here. So Jun, certainly if you want to manufacture it and insist on open walled structures, then for the stiffness objective, you would not need microstructure. Then the best structure would be a solid structure. So open walled microstructure is only the result of the optimization if you either insist on a certain porosity, or if you have some other goals like fluid flow or something like that, right? So you have to pose another optimization problem if you want microstructure to appear if it cannot be closed walled.
Yeah, I understand. I understand from the optimization it will the closed wall structure will appear. I was just wondering whether there are some ways to manipulate this formulation to encourage porosity or to encourage the walls become open.
Yeah, but then you would have another optimization goal than stiffness
Yes.
here. But definitely the Phasor approach wouldn't mind doing something with open walled. In fact, you have a nice picture in your thesis, Rebekka, where you show that any microstructure can be realized using the Phasor approach.
Yes. So, okay, so then I'm with you. Yeah, no, it depends a lot on the input, right? I mean, the Phasor noise is very flexible, but the way the current method is designed, it's designed to reproduce what it's given. So you need to give it what you want to start with.
Yeah. Any other question from the audience? If I look at the time, it's 2 minutes past 5. If there are no more questions, let's conclude the session today. Thank you, Shelly and Rebekka, for joining me in this multiscale topology optimization session. Thanks for the wonderful presentations. And it's great to see so many familiar faces.